Okay, so for many of these questions, maybe not all, what you're typically given is an ordered pair P. So P is some point with X and Y. So maybe it's, let's just go simple 1 and 2, right? So what this represents, and we'll go into more and more detail as we do examples, but what this represents is an ordered pair, right? So that means this is your X value and that's your Y value. So if we were to plot that, where would this point normally live? That's usually where you start, right? Well, just as an ordered pair, we would move over one space for X and up 2 spaces for Y, and then we'd put a point here. Now what that means is when it comes to your actual graph, you're starting in standard position, and your terminal side goes through that point, right? All you need to draw a straight line is 2 points, essentially connect the dots, and this is a ray, right? So we're going to keep going through that point. So you've got this value for theta from here to here, okay? Now, I drew this a little small, so I am going to need that space. So now what we want to do, let me just squeeze theta in right here. So now what we're going to do with this is we're going to create a right triangle. So from this point, from P, right, that's P, from this point, we're going to go straight down, and it should line up with your X value, which in this case is 1, right? By going straight down like that, we've created a right angle, which again gives us a right triangle. Now, because mine is kind of tiny, I'm just going to draw it off to the side here, a little larger. And good thing that corrects my right triangles, right? So the pink side that we drew is back here, right? Theta is right here, and the value of P is located here. All right, 1, 2. Well, this point lines up with the origin, right? So our goal here is, can I represent the sides of this right triangle, even though it's not technically a right triangle because this side keeps going, right? And because this side keeps going, we're going to pretend that's straight, keeps going as well. It's just that this snapshot I'm taking is a right triangle. So can I figure out values of these side lengths? Well, yeah. How did we get the triangle to begin with? Well, we used ordered pairs X and Y. So that means this marker right here is 1, which may be better stated as this entire side length here is 1. Same thing for Y. How did we get our graph? Well, we went up 2 spaces for Y. That means that this vertical length is equal to Y, which in our case is a 2. So how could we go about finding what we've named R? So I'll put X down there. I'll put, sorry, there's still fireworks going off. I'll put Y there, and I'll put R right here. How can we find that value of R? Well, that's just a hypotenuse, right? Apply your Pythagorean theorem, right? So you've got, I'm going to call this R because that's what we tend to call it for this definition. So we've got R squared is equal to 1 squared plus 2 squared. So you've got R squared is 1 plus 4, R squared is 5, which means R is, again, I drop the plus or minus, and it's just square root 5. Well, that's this value out here. So what we're interested in, and I'm going to go into more detail with this, like I said, in the next video, but what I'm interested in is, can I generalize this? What if I didn't know the specific numbers that make up this ordered pair? Which means I don't know that's 2, I don't know that's root 5, and I don't know that that's a 1. And all of this is no good, right? If you didn't write that down, pause the video and rewind it, write it down. What if I don't know any of that, right? What if this is still just a generic X and a generic Y? Can I still make the same representations? Yes. So this horizontal value down here, this bottom leg of our right triangle, is still X, whatever X may be. Our vertical length is still Y, whatever y may be. And I can still name this r, but I can actually do a little bit better when it comes to defining what exactly r is. Let me scoot over for this. So if I use that same exact Pythagorean theorem, and there's two ways we can do this. So we can either say the Pythagorean theorem, right, which says r squared is x squared plus y squared, right? If I was to solve for r, I would say r is x squared plus y squared underneath the square root. Again, I'm going to assume r is a positive value. I can actually go further than that. I could, well, positive is fair. R is a positive value. This is slightly more formal in how we're defining it. So this is better, for lack of a better word here. It's a little better for us to actually use the distance formula. So distance formula in general is the distance between 2 points is the difference between them, so x2 minus x1 squared plus y2 minus y1 squared. Hopefully that's familiar. If not, jump on YouTube, grab a quick video on the distance formula. The 2 points we would be using here, I called one of them x and y, and the other one is actually just the origin, right? So this distance, and I can go a little better than that, I can say r, because r is the distance we're talking about here, right? R is equal to my one value x minus my origin plus my other value y minus my origin, but x minus 0 is just x, right? So this is just x squared, and y minus 0 is just y, so y squared, and that's the exact same thing as over here. So like I said, technically that distance formula is a little bit more on the nose as far as how we find it, but it's completely related to the Pythagorean theorem. So a common mistake that I see here, I see a lot of people put a subtraction sign here when it's adding. And so if it helps, remembering that this comes from the Pythagorean theorem and the Pythagorean theorem addition in the middle, maybe it can help you remember that that's addition, right? But like I said, it's good to still know that it comes from the distance formula and that these are all interconnected with each other. So in the next video, we'll go over a specific example of how to finish a question like